Hey everybody, we are back. In this segment, we're going to talk about how to conduct a hypothesis test for the population mean when we have to estimate sigma. We don't know the population standard deviation, so we're going to wind up estimating it from sample data. And recall, we've seen this situation before where we had to use some small sample assumptions here related to the t-distribution. And that is really the framework we're going to be in here, is thinking about utilizing the t-distribution in cases where, we have a sample, there's fewer than 30 observations, so we cannot apply that central limit theorem. And in this case, the only difference really is that instead of computing z-scores, we're going to be computing t-statistics here, where you'll see S replaces sigma. So instead of the population standard deviation, we have the sample standard deviation showing up. Recall that the t-distribution looks a lot like the normal distribution. It's symmetric, it is bell-shaped, but it does have fatter tails, a little bit different kurtosis property than the normal distribution does. As the sample size gets larger, that t-distribution does approach the normal distribution in the limit in its shape. Now we're going to jump right into a case study here, looking at an internet business that would like to determine the average income of its customers. In a randomly selected sample of 10 customers, the following incomes are reported, and these are measured in thousands of dollars here. So we have a sample size of 10. Obviously, we can't apply the central limit theorem here and assume that that sampling distribution is perfectly normal. So in this case, we're going to go ahead and use the student's t-distribution to compute our sample statistics. So what we want to do here is we want to test the claim that the mean income of the company's customers exceeds $50,000 at the 10% level of significance. So that's what we are trying to show here. And here's what we know. If you were to compute the sample mean from this data set, you would see it as 65.4, $100,000 really. The sample standard deviation is about $22,000. So here are the summary statistics for this small data set. And again, the population parameter of interest for us in the context of this narrative is the mean income of the internet business's customers. Okay, so here is the setup of the problem. Now, again, we want to test a claim, okay, and we're given now a small sample data set, right? There's only 10 observations here. Okay, and if we're using the t-distribution, we know we're looking for the t-distribution. We're going to use the t-value to figure out our critical threshold now instead of the z-table. And we're going to use 9 degrees of freedom here, which correspond to a sample size of 10. Remember, the number of degrees of freedom is equal to n minus 1, the sample size minus 1. So again, we're trying to show here that the average incomes are sufficiently large, that they're high. So this is going to wind up being a one-sided, really a right side tail test for us. So if we were to go ahead and go to our t table now, we could figure out the associated t value here. So let's go ahead and do that. We're looking for the row where we have 9 degrees of freedom. And we're using now a 10% level of significance for a right-tailed test. So let's go ahead and take a look at the t-table in this situation. Okay, here is what it looks like. And again, we are interested in a right-tailed test. So note this picture right here describes how we would run that right-tailed test. Okay, and we're looking for this alpha prime value. So you'll notice up in the columns of the t-table here, okay, there's 3 different rows that define these different columns. We've used the top row before to look for confidence interval thresholds, but now if we just have a one-sided right-tailed test, okay, we're going to use the alpha prime row here. And again, alpha was equal to 0.1, was 10% in our example. That was the significance level we were using. We had exactly 9 degrees of freedom corresponding to that 10% level of significance, which means the t-value that we would use here to define our critical value threshold is going to be 1.383. So we're just using the t-values to get our critical value threshold instead of the z-value, because we're not using the normal distribution anymore. We're using the t-distribution for a small sample, smaller than 30. Okay, so now we have that t-value. We can go ahead, plug it in, and we can define here our decision rule. Okay, what we've done now is we've thought about what is this t-value threshold, okay, that little t sub alpha threshold there, above which we would be far enough away from the mean to say that we can reject the null hypothesis that the average income was pretty low. Okay, so again, we were looking for that t-value, right, associated with 10% in the upper tail, okay, which means it only leaves a 40% probability in there, but we actually didn't need that number here given the way that the t-distribution table is set up for us. So at this point, we can think about our null and our alternative hypothesis. Since we're trying to show that the average incomes are pretty high, and remember, what we're trying to show is really the alternative hypothesis. So the null hypothesis, then, what we're going to disprove is that the incomes are sufficiently low, that they're lower than $50,000 on average. That's what we're trying to disprove. So we're looking, again, for high values of a sample statistic for us to be able to say, no, that null hypothesis is wrong. The observations are not smaller than or equal to $50,000 on average, in favor of the alternative hypothesis that says, yes, they are above $50,000 on average. So in this case, our decision rule here, we can specify that as saying we would reject the null hypothesis if t, our test statistic now, using the t transformation, right, similar to the z transformation, but with s instead of sigma, using that sample standard deviation. Okay, the decision rule says we are going to reject the null hypothesis if our test statistic falls farther to the right than that 1.383 critical value threshold. And otherwise, we will not reject the null hypothesis. So at this point, all we need to do is take our sample data, compute this test statistic. Okay, so I'm going to plug in x bar, mu, sample standard deviation, and sample size into that expression. And once we do that, and once we plug everything in here, then we can go ahead and we can compute that test statistic. Okay, so we see it's 2.194, and we're going to reach a decision, and we want to be able to interpret, of course, the result here. So you might already be saying, hey, 2.194 standard errors to the right of the mean. That's really extreme to the right, given our threshold was only 1.383 standard errors to the right. So the decision rule here is going to involve us, given our rejection region and given our critical value threshold, our test statistic was to the right in that rejection region. So the conclusion here is we're able to reject the null hypothesis in favor of the alternative. Based on our observational data, there is statistically significant evidence to conclude that that mean customer income does exceed $50,000. So let's go ahead and take a look at another example here when we have a two-sided, a two-tailed test. And in this next situation, we have Celebrity Living claims that the mean sales for personality magazines that featured such people like Angelina Jolie or Lady Gaga are 1.5 million copies per week. So not greater than, not less than, right? Null hypothesis here is going to be that they are selling 1.5 million copies per week. A sample of 10 comparable titles shows a mean weekly sales last week of less than that, of 1.3 million copies. So our evidence says it looks like things are lower, at 1.3 million copies, with a standard deviation of 0.9 million copies. Let's assume that the population distribution is normal, and we're going to use the 1% significance level here. So again, notice we have a very small sample size, just 10 comparable magazine titles, right? Just 10. And the first question we always want to think about is, what is the population parameter of interest? And here's the information that we're given. But we're being asked about not the number of magazines, not specifically about which celebrities are featured. We're being asked about the average number of magazines that feature popular celebrities that are being sold every week. Okay, and we're now going to think about the appropriate null and alternative hypotheses here. Note that our sample evidence is showing that this is a little bit lower than the claim. All right, so our claim here, that 1.5 million copies per week are being sold, that is going to be our null hypothesis. And again, remember, the null has to have some form of the equality when we're talking about hypothesis testing for the mean. So that eliminates both C and D almost immediately, right? There's inequality symbols there. So we're between A and B, and A is the correct choice here, that the claim that we're testing is there's 1.5 million copies per week being sold. And we can see that the sample evidence is already suggesting that there's maybe a little bit of difference there. And we want to figure out, is 1.3 million copies sufficiently different than 1.5 million copies? Now note, when we're dealing with an equality hypothesis, where the null hypothesis is mu equals a value, okay, and the alternative is it doesn't, then in order for us to find evidence to support the alternative, there's two types of evidence we could find. We could look for values that are really small relative to the null, or we could look for values that are really large relative to the null. In this case, the evidence suggests we're going to go in the left direction here, but this is a two-tailed test due to the specific form of that null hypothesis. Okay, so we have to figure out what is the decision rule in a moment. And we want to think about our accept and reject regions here. Okay, so if we are using a significance level of 1%, and this is a two-tailed test, and we have a sample size of 10, that means we're going to be finding the t statistic that defines our critical threshold value here, which is going to have 9 degrees of freedom, right? N minus 1 degrees of freedom. And we can go ahead and take a look at our standard, or at our t distribution table, where we're looking for a two-sided test here with a 1% level of significance. So remember, if it's a 1% level of significance, we're going to wind up really dividing that up into each tail of the distribution. So there's going to be 0.5% left in each tail. Okay, so let's go ahead and take a look at our t table to see this. So here we are at our t table, and we were using 9 degrees of freedom specifically. Okay, so our answer is going to be somewhere in this row for the relevant t value we're going to use that are going to define these thresholds here. And you'll notice, since it's a two-sided test, we're actually going to use the first column just like we did when we were describing confidence intervals, okay, using the t distribution. So 1% level of significance, remember that corresponded to a confidence level of 99%, way over in that far right column, since we're using a two-tailed test. And again, if you look carefully at how this table is set up, it's telling you what those 3 different rows above the table mean. Okay, the first row is about confidence interval, which is associated with the two-tailed test. We're going to discuss that in the next segment. Here it is for the right-tailed test. We're using alpha prime, and for the left-tailed test, we can also use alpha prime there. Okay. Two-tailed test here, alpha double prime. Okay, so we could use this third column, or we could recognize the relationship between the confidence interval here. So let's take a look at this alpha double prime column and make sure we can see what's going on. So if we look here at this row of the table that defines these different columns associated with alpha double prime, that is really the significance level corresponding to a two-tailed test here. And so this is the picture we want to use to tell us where to look on the table. We're looking at alpha double prime. It's going to give us the t-value thresholds on either side of the mean for the two-tailed test. And we were using a 1% level of significance. So remember, 1% level of significance, that's very much related to this 99% confidence interval value. In fact, the t-values, or the t-value thresholds we're going to find, are all associated here. So if we look across our row of the table where we have 9 degrees of freedom, and where that intersects with this column where we are using a 1% level of significance for the two-tailed test, right, using this alpha double prime to define our column that we're looking at, then the relevant t-value for us becomes 3.25. That is the relevant t-value threshold. So let's go ahead and jump back to our example here. Okay, we now have the t-value threshold found. It is 3.25. So we can go ahead and answer this question. Our decision rule is going to be to reject the null hypothesis if we get a test statistic that is more extreme than 3.25 in either the positive or the negative direction. Okay, and what we need to do next is compute the test statistic given the information that we have here. Okay, so here is our x bar. We're going to subtract mu, and we're going to divide by s over the square root of n. So if we do that, okay, the test statistic we wind up with, and you can pause the video for a moment and compute it yourself if you'd like, is going to come out to minus 0.7. Okay, and that should make sense because our sample evidence was a little bit lower than the presumptive mean, which was 1.5 million here. All right, so now we're in a position to go ahead and think about the rejection region and making our conclusion. So what is the conclusion we're going to be able to draw here? Well, hopefully you've seen that the test statistic is not quite as extreme as our critical value thresholds that we had found before. So again, here is the picture that describes our situation. We have found these T thresholds here that have associated values of plus or minus 3.250. Right, so this is minus 3.250. This is plus 3.250. And our test statistic does not quite make it far enough to be extreme in this distribution to be considered a value of evidence that would cause us to reject our null hypothesis here. It's not extreme enough, right? How far is far? Not in that rejection region here. So in this situation, we're going to fail to reject that null hypothesis in favor of the alternative hypothesis. So is there sufficient evidence to conclude that the mean sales for personality magazines that feature popular people are 1.5 million copies per week? Well, we cannot reject that null hypothesis. We were not given enough statistical evidence to reject it. Okay? So we haven't proved that it's 1.5 million, but we cannot say that it's not with the amount of evidence that we have. So this was us looking at a couple examples here of how to compute the hypothesis test, how to run a hypothesis test when you're dealing with a small sample set of data. Let's go ahead and look at one more example here. Where a credit manager claims that the average account of customers is $410, and an auditor takes a sample of 18 accounts and finds the mean is actually much higher. The evidence says it's much higher, $511.33. And the standard deviation is $183.75. Question is, if the sample results are not supporting the manager's claim, then the auditor is going to have to go back and check all the company's accounts. And this is a costly process. We're going to assume that the population is normally distributed here, and the significance level for the test we're going to run is at a 5% level of significance. Okay. So we're going to have to run the full test here to think about this, which means we have to know our null hypothesis and our alternative hypothesis. So let's go ahead and think about that for a moment. And again, we're given some information to start with. Now, null hypothesis here, okay, is the claim that the average accounts is exactly equal to $410. Okay, so again, we're going to be dealing with a two-sided test in this situation. Okay, which means we could look for evidence, sufficiently greater than 410 or sufficiently smaller than 410. But it looks like the sample evidence that we've collected here says we're going to be looking for evidence in the right direction, in the right side. Tail here, 511.33 is larger than that mean of 410. Okay, so what we're going to need to do here is figure out using a two-tailed test. Okay, we're going to have to figure out what is the threshold T value that is going to define the critical values. So let's go ahead and figure out the T value threshold given the form of our null hypothesis, which tells us it is a two-sided test. Okay, so let's go ahead and go to our T table here. Okay, and again, we're looking at a significance level of 5%, but it is a two-tailed test. Okay, so we're going to be using that alpha double prime to identify our column again for the two-tailed test at the 5% significance level. And we have a sample size of 18, which means we're going to be dealing here really with 17 degrees of freedom. Okay, we're going to have 17 degrees of freedom. So we're looking across this row. And To figure out the column we need to look at, we're using 5% level of significance for the two-tailed test here. So we're going to go straight down this column to the row where we have 17 degrees of freedom, and that tells us we're going to be using a t-value of 2.110. So back to it. Here, our t-value is 2.110. Now what we're going to need to do is compute our test statistic for that sample mean. So we're going to use that 511.33 value. We're going to demean it relative to mu. We're going to subtract 410 from it and then divide by s over the square root of n. So if we do that, we wind up getting a test statistic of 2.34 standard errors away from the mean in the right direction, in the right side tail here. And note that is definitely larger than the critical value threshold of 2.11. If that is the case, then we are far enough away to say that the sample evidence is sufficiently different than the hypothesized value under the null. And in this case, we should be rejecting the null hypothesis. And then that means the auditor should proceed to check all of the accounts given the narrative. So hope that was fruitful. Looked at a couple examples of implementing, again, the t-distribution and running a hypothesis test for the mean using a small sample where we could not exploit the central limit theorem. And in the last segment, we will talk about the p-value approach to hypothesis testing, as well as a little note about the relationship between the two-tailed test and our structure of our confidence interval. See you then.